Okay, in this example we're trying to understand how the two-span beam is going to respond, in this case to a full live load along the entire bridge. We're going to put the live load all the way across because we're going to focus on what happens here at that middle support in terms of the negative moment, but we also care what happens elsewhere in the beam in terms of the moments and the deflected shape. Right? So the first thing we're going to do is we're going to work on anticipating what the results might be for this moment diagram. And as we get into that, notice the shape that has been drawn here. In this sort of two-span situation, we anticipate this sort of gull wing type of shape. If we had many spans, every one of these middle supports would have typically a negative moment here. That is, if it's fully loaded in each and every one of the spans. The question starts to become, well, why is this moment in one span maybe different than the moment in the other span? And I got a classic shape here, this curvilinear shape, and where's that coming from in my approximation or my guess, anticipation of what's going on here? Well, one of the things you might naturally kind of figure is that the span in the moment in the longer span is going to be larger than the moment in the shorter span. It sort of makes sense if these were simply supported as in not connected to each other here, this intermediate support, and with this distributed load, the max moment would be WL squared over 8 in each one of those two spans. So that's telling us that the moment is sensitive to the span length squared for the distributed load kind of situation. So it would make sense here that we might guess that M1 is greater than M2, that the longer span moment is larger than the other one. Right? We should also anticipate this second order shape that we've got because remember that the second derivative of the moment is equal to the distributed load intensity, and since that is a constant, then that means, of course, when you integrate that load twice, then you integrate a constant twice, you're going to end up with a function of x squared. In other words, a parabola type shape in each one. Right? Doesn't necessarily explain why we might end up with a negative moment at this interior support, but that'll be sort of a classic situation, and we will see that directly in a little bit about why that happens in this particular situation. But you could anticipate the following, and that is, from the deflected shape, we would expect that in each one of these spans, in the middle of them, that those beams want to try to go downwards. And if they're going to go downwards, that's great, except for we've got the support here in the middle that wants to keep it from having any displacement at all. So we'll be draping through those two regions. So we'll have smiley face deflections, concave up curvatures in both of those spans. That's these positive moments here. But as it goes over the support, because it's continuously connected, it is not a broken beam, it doesn't have a hinge of any sort in there, then it's going to drape the other way, or what we call hogging curvature, and so that's going to create that negative moment over that interior support for the typical case of having that live load all the way through. Right? And so then if we kind of wrap back here, note that because those span lengths are not the same, we do expect not only different peak moments as we mentioned before, but we'd also expect some level of asymmetry in all of the response quantities. We don't expect the reaction at A and the reaction at C to be the same. We don't expect the maximum deflections wherever they occur in those spans to be the same. The max shears are not going to be the same. That asymmetry here is only being created by the span length, and we expect that to have ripple effects all the way through the rest of our prediction of the response.